So the first thing to make sure is clear when talking about the moment of inertia is that it goes by two names. So the moment of inertia or the rotational inertia are talking about the same thing. So with that in mind, that obviously brings us to the question, so what is the moment of inertia or the rotational inertia, whichever one we choose to call it? One way to answer that is to say that it's a measure of how easy it is to get an object to rotate. So in some sense, this is the rotational analog of mass. We said that mass was a measure of how easy it is to accelerate an object. The rotational inertia is a measure of how easy it is to change how an object is rotating. So this is going to depend on a couple of things, the most important of which is it's going to depend on how the mass of the object is distributed relative to some axis of rotation. So what will happen is we'll say the moment of inertia of an object. What we will always mean, even if we don't explicitly say it, is the moment of inertia of an object about a specific axis of rotation. So the axis of rotation always matters anytime we're talking about the moment of inertia. So the moment of inertia cares about the axis that you're trying to get your object to rotate. Now, the shape of the object might matter. And so the idea here is, let's take two examples dealing with let's say, the moon. So one is when the moon is orbiting the Earth. So here's the Earth. This dot is the moon. In the context of this distance between the moon and the Earth, I don't really care what shape the moon happens to have, right? It happens to be basically spherical. But the honest statement is its shape could effectively be anything. It doesn't really matter for the calculation I'm going to do because the size of the moon is really small compared to the distance that separates it from the Earth. On the other hand, if I want to talk about the moon rotating about its own axis, well, now it's much easier to see that the shape matters here. So whether the moon is a sphere or a cylinder or a hollow sphere or anything else, right? So this is a situation where now the size of the moon is on the same scale as its distance from the axis of rotation. So again, I do care now about its shape. So if the shape doesn't matter, let's start there. Well, largely if the shape doesn't matter, that means either you've got point particles or you can treat things as point particles. So again, the moon is clearly not a point particle. But if what I'm interested in is the moment of inertia of the moon as it rotates about the Earth, as it orbits the Earth, well, I can treat that as if the moon were a point particle. And so my equation for calculating the moment of inertia or rotational inertia of a point particle is given right here. So I, so our moment of inertia, is equal to mass times our perp here is this perpendicular distance from the mass to the axis of rotation, and that gets squared. So let's say, just as an example, I've got a mass, it's on the end of a massless string of length L, and I'm swinging the mass around in a horizontal circle. Well, the axis of rotation is clearly the center of that circle. And so the perpendicular distance from the axis of rotation to my mass happens to be simply the length of the string. So when I go to do the calculation here, this one's pretty easy. I just get that the moment of inertia for this mass, treating it as a point particle as it goes around in this horizontal circle, swings around in this horizontal circle on the end of the string of length L, is just ml squared. What are the units of this? Well, the units of moment of inertia, right, just looking at my expression, are going to be the units of mass, those are kilograms, times the units of a distance squared, so that's meters squared. So the units of moment of inertia will be kilogram meter squared. So let's change it up a little bit. So same mass, same massless string of length L, but now instead of having this go in a horizontal circle where the whole string is in the plane, now what if I let this hang down so that my string makes an angle theta with the vertical? Well, again, the axis of rotation here here's the axis of rotation. So what this means is that the perpendicular distance that I'm interested in now is not the entire length of the string. And in fact, it happens to be fairly easy to see that that perpendicular distance is just going to be L sine theta. So when I plug this in to calculate what the moment of inertia is now, I get mass times perpendicular distance squared is just going to be L sine theta squared. So this is how I treat things as point particles. If I've got multiple point particles, so again we've started talking about systems, and so if I've got a system of point particles, what I am told is that the moment of inertia of the system is just the sum of the moment of inertia of each particle. So in the same way that we would say the total mass of our system is just add up the masses, well, the total moment of inertia of your system is just add up all the moments of inertia. So here in this case, again, let's say I've got two masses on the end of massless strings, and so they're going around in some circle here. Again, I can figure out what the perpendicular distance from the mass to the axis of rotation is for mass 1, what the perpendicular distance from the mass to the axis of rotation is for mass 2. And so again, I just now need to calculate each individual moment of inertia, right? mr perpendicular squared, and then add all those up for each of the particles that I have. So you keep adding more particles, great. I just add more terms to calculate the moment of inertia of my system. So all these are situations where the shape didn't matter, right? I could treat things as point particles. Well, obviously there are going to be plenty of situations where the shape does matter. So for situations where I have a uniformly distributed object where the shape of the object matters, largely what we're going to do is we're simply going to look up what the moment of inertia is. And so here's a table. There's one in your book as well. But largely what we do is we pay attention to two things. One, have I got the right object? So let's say I want a long, thin rod or a slender rod. And then I also, in some of these tables, will need to pay attention to what's the axis of rotation. So notice for my slender rod, it gives me both the moment of inertia equation for the axis through the center. Right? Here's the yellow line here is the axis through the center. And it also gives me the one for the axis through an end. So I'll need to pay attention to both, do I have the right shape and do I have the right axis of rotation? So you notice that for these spheres, here's a thin-walled hollow sphere, right? That's another way of saying a spherical shell. Here's its axis of rotation about its center. So the picture's showing me here clearly that the axis of rotation runs through the center of the sphere. Here I have a solid sphere, its moment of inertia, again about an axis through the center of the solid sphere. Same thing for a cylindrical shell, a thin-walled hollow cylinder, or a solid cylinder. Again, axis through the center. So the last piece is, well, what if I've got an object that's made up of multiple parts? So here's a situation where, let's say I've got a mass 1, mass 2. They're connected by a rod of length L that also happens to have a mass of M3. So I've got two things that I can treat as point particles, and then a third object here that is part of my system that I can't treat as a point particle, right? I care about its shape. Well, again, what I'm going to do is I'm basically just going to say that the moment of inertia for my system is just going to be the sum for each piece that makes up my system. So I can break up my system into pieces and calculate the moment of inertia for each piece, and then I just need to add those things together. So in this case, I've got a point particle, so this will be mr perpendicular squared. Here's a second point particle, so this will be mass times r perpendicular squared. I'll go look up what's going on for my long, thin rod of length L and mass M3, and then I just need to calculate what all those pieces give me. And so in this case, what I get is a M1. Here, my R1 perp is half the length of the rod. So here's my mass 1 as a point particle. For mass 2, its R perpendicular is also half the length of the rod. So here's the moment of inertia for mass 2, treated as a point particle. And then going and looking up for my long, thin rod, rotating about its center of mass, that happens to be 1/12 ml squared, where I plug in the right mass that I need for So if I've got multiple, or if I've got a more complicated object, then all I'm going to do is basically break it up into the simple pieces that I know how to calculate, and then just go ahead and add together the moment of inertia of each of those pieces to get the moment of inertia for my total system.